Hi, I'm Gatia here. I did my final DSA project on understanding the data structures and optimizations used by large data retrieval systems. So, information retrieval is just the problem of returning documents that match a query. It isn't a new problem. Librarians do it, the index at the back of a book does it. It's a pretty simple task. However, scaling it to work on big data is a real challenge. There's tons of ongoing research into making information retrieval faster and more compact. Here are some examples of information retrieval applications. From a high-level overview, information retrieval systems have three parts: indexing new documents, retrieving documents, and ranking how well documents match a user query. A huge information retrieval system like Google finds new documents with a crawler that traces page links, performs fast retrieval by using an inverted index data structure, and performs ranking with artificial intelligence. Let's focus on the inverted index data structure. You can think of an inverted index as a hash map, where the keys are the terms and document IDs are the nodes. It scales really well because it has a constant lookup time per term. It is called an inverted index because the normal index is the map of document IDs to words in the document. So the big problem that shows up when dealing with a gigantic corpus is you need a huge number of unique document IDs, and storing those huge numbers takes up a lot of space. For example, if you Google the word "the," it returns 25 billion documents. Just to store those document IDs requires more than 200 gigabytes. To lessen memory usage, information retrieval systems use compression codes that map large document IDs onto smaller integers that require less bits. Here's a chart of the trade-off between space savings and decompression time cost. Information retrieval systems need compression codes that save space and decompress quickly. Elias-Fano is the most common compression code used by information retrieval systems. Most codes only support sequential decompression, so they aren't great for information retrieval systems. In contrast, Elias-Fano supports very quick random access while also maintaining a good compression ratio. It's quasi-succinct, which means that space compression is close to a theoretical bound, and its fast non-sequential decompression depends on two operations: rank and select. Here's how Elias-Fano compresses sequences. Here's how quickly and non-sequentially decompresses sequences using rank and select. Partitioned Elias-Fano is an improvement on Elias-Fano that takes advantage of naturally occurring, highly compressible clusters of document IDs. So normally, when a crawler follows page links to find new documents, it forms these natural clusters of consecutive document IDs because linked documents frequently use the same vocabulary. Consecutive sequences are way more compressible than random numbers. Partitioned Elias-Fano breaks the sequences into chunks, stores pointers to the start and end of chunks, and compresses the pointers with Elias-Fano. This lets it get double the compression while keeping the same lookup speed. Partitioned Elias-Fano needs to quickly find the best places to draw partition lines. This is normally an exponential time complexity search, but with a combination of dynamic programming and directed acyclic graph sparsification techniques, Partitioned Elias-Fano does it in linear time. Finally, I'm going to talk about BitFunnel, an alternative to inverted indexes. Adding a new document to an inverted index is a costly global operation that requires updating the postings list for each term of the document. That's why inverted indexes usually use batch updates. However, sometimes you want to search on documents that haven't been batch updated. For example, people want to see news updates immediately when they get posted. The Bing search engine uses a compact data structure called BitFunnel to allow fast querying on documents that are waiting for the batch update. BitFunnel uses Bloom filters as a compact way to represent the terms in a document. Bloom filters are a probabilistic data structure, so they can return false positives. The BitFunnel data structure is a bit slice table of Bloom filters. In this representation, each document has its own column. This allows new documents to be added with a quick local update. BitFunnel uses intelligent corpus sharding and weighted Bloom filters to reduce the false positive rate while further reducing memory usage. Any false positives that remain can be eliminated by the machine learning algorithm in the ranking stage. Thank you for listening to my presentation on inverted indexes, Elias-Fano, Partitioned Elias-Fano, and BitFunnel.